Hello everyone and welcome to our very first class. This is going to be Solar Power 101, the ultimate beginner's guide. My name is Patrick and I'll be the instructor for this series of videos. And today we're starting with our first topic, which I think is going to be our most important topic as far as the number of people this can reach and actually help. This is definitely the most common question that I see, and it's asked in a bunch of different ways. A couple of examples would be, can I buy this solar panel, or what is the best solar panel for X, Y, and Z? How many solar panels can I connect to X, Y, and Z, or will this work? When we think about solar setups, a lot of people probably think about what's on the wall over here. Individual components, someone who's actually building a solar system. The reason this is also such a common question is because it reaches the common person. Your everyday mom and pop can go into Costco and pick up an EcoFlow Delta, and they might be buying it because it's advertised as UPS or power backup, things like that. And they bring it home, not realizing that they just brought home something that is a solar appliance. And perhaps they didn't buy it with the intention of adding solar to it, but then once they got it, they're like, oh, that's really neat. It has solar panels on it. And then they went and now they don't know how to figure out what kind of solar panel to get. So if you're one of those people, we've got you covered in this video. So what's important to know about sizing an MPPT and solar panel together? The most advertised specs that you'll see when you're purchasing equipment is ironically not the information you need to know. Remember, their goal is sales. So they're going to throw sales figures at you. So they're going to throw the big number like the output wattage of the inverter or the maximum wattage of the solar panel. They're not going to give you all these little finite nerdy specs because they don't really mean anything to most people. But someone who is designing a solar setup, the engineers, for example, those are the only figures they actually care about. But you as an educated consumer, you also need to know about those numbers. So on the sales page, when you see the panel wattage, technically that doesn't matter for this step, the sizing step. And also technically if you see the output on one of the all-in-one units, that doesn't matter either. Those things do matter when it comes to sizing your system for your actual demand, the needs of the system. So you need enough solar panels to charge your batteries every day. And you need enough inverter output power to run whatever your desired loads are. But it has nothing to do with actually sizing the solar panels to the MPPT. So that's what we're going to talk about to start with. So if the stuff that's right in front of you is not what's important, then what is? What is it that you actually need to know that everyone is missing, right? On solar panels, which is where we're starting, it's the VOC, which is your voltage open circuit, and your LSC, which is your short circuit current. In addition to that, things that are kind of important would be size, weight, and cost, because just due to the fact that the solar panel can be a perfect fit for you electrically doesn't mean that it's going to work for you if it's too big, if it's too heavy, or it costs too much. And you do need to shop around because you can find similar items vastly apart in cost. So that's why sometimes you might go ask for recommendations because people might have a little bit more knowledge on what's on the market that's a good value and reliable. The critical terms, VOC and LSC, what are they? The VOC is basically what you would measure from a solar panel if you took it outside in the sun, took a multimeter and just hooked it up to both of the outputs and measured the voltage. It is the voltage that panel produces in a worst case scenario or best case scenario, depending on how you look at it, when no load is connected. So it's the highest voltage possible on an open circuit. The LSC is basically the same thing, but you go to that solar panel and you connect both of the connectors together and create a short circuit to the panel. And then that is the maximum current that the panel itself internally will support. So you basically have the highest voltage and the highest current. Those two figures are the figures we need to use so we can determine the worst case scenario to fit the solar panel to the MPPT without overloading it. So we can talk about it all day long, but you need to know what you're actually looking for. We need practical examples. So what I did is I just went to Google and I searched solar panel specs and I grabbed the very first two images that came up that actually had the specs that we're looking for. So no hand picking, these are just real life examples. So this 420 watt portable solar panel, let's go ahead and mark this up in real time. Here's what I warned you about, this number. This is the number that a lot of new people might come in, say, this is a 420 watt panel. Does it work with my Blink, whatever that might be, Delta, MPPT, Victron? And the answer is we don't know, and you don't know, because this number isn't going to give us the information we need. Just below that are your numbers that might fool you. The maximum operating voltage and the maximum operating current. These are your best case scenario real life numbers. So what you might expect to see from the solar panel when it's hooked up and functional in a best case scenario. But generally speaking, you won't even see these numbers. You're going to see less than these numbers. Some solar panel companies are nice enough to give you not just max operating, but also like average operating. So there you go. Those are not the numbers you want. Very specifically, just below that, you'll see the open circuit voltage and the short circuit current, the VOC and the LSC. These are the numbers we actually need to get. And what I want to point out real quick is just look at the difference here. A maximum operating voltage of 40.3 versus a VOC of 48.9. You see how dramatically different those numbers are? So you can just imagine if we're talking about a solar panel array of 10 panels, how large that voltage difference would be if you calculated with the wrong figures. So that's why it's very important to understand exactly what figures you're looking for and not make a mistake there. Moving on to our second practical example, this is more like what you're going to find on the back of a solar panel. There's usually a sticker on the back, some kind of foil sticker, and these are the specs that you'll generally find on the back. So it's the same story here. We don't need wattage. We don't need these maximum standard. We're looking for the VOC and the LSC, which are the last figures here, the 47.7 and the 11.51 amps. So those two numbers are the numbers you would write down for the next step of calculating how many of this particular solar panel will fit with your particular equipment. So that should cover our bases when it comes to solar panels. What we're looking for here is just those two simple things, the VOC and the LSC. But that's only half of the equation. We're matching the solar panels to the MPPT. So what about the MPPT itself? What are we looking for there? Because obviously we have to have something to compare against, right? So let's do the exact same exercise about what's important on the MPPT. The critical things to know, instead of two, now there's actually three things. Two of them are basically the same as the solar panels, the maximum voltage and the maximum amps. We still need those same two specs as before. But this item is new and extremely important. The battery voltage and the type of battery that it was designed to work with actually matters a lot. So whether it be an inverter or an MPPT, an all-in-one, it will be designed to work with specific battery chemistries because these are just battery chargers that use solar panels as the charging source. So they have different settings, so to speak, for each type of battery, because an old school flooded battery does not charge the same way as a new school lithium battery. So you have to have an intelligent charger that knows the difference. And of course, the voltages can be different. So a battery charger that's only designed for a 12-volt battery would absolutely not work with a 48-volt battery. So for that reason, just for things to be compatible, you have to ensure that your whole system is going to work together by matching up all of these things. If you're designing a larger system, the higher voltage is going to be easier to work with because it's going to give you higher powered inverters. It's going to give you more options for high powered inverters. It's going to give you the opportunity to work with higher voltage and lower current, which means smaller wires because the wire size will be based on the amount of current. So just a little bit of, foreshadowing that when you're designing your system, think ahead several steps so that you can provide yourself the best solution up front. So let's move on to our first practical example. It's the same as before. I just grabbed the first two images that popped up on Google and said, all right, that'll work. We'll go with it. And the very first one actually ended up being a Victron. So I like Victron. That's what's on the wall over here. They've been extremely reliable. They have a big following. I like them a lot. So I think this is a good example. The other reason why this is a good example, besides they're so popular, so you might be buying one, is that they're a little bit different. Victron doesn't necessarily notate their specs the same as most of the other manufacturers. So let's start by looking for our three things, right? Battery voltage, it's right here on the first line. 12 volts, 24 volts, 12 volts, 24 volts, and 48. You can see These are basically the same model, but they added a new version of it just to pick up support for 48 volts. So if you had bought this with the intentions of using a 48 volt battery, you would be in a bad place. So the other two things we're looking for, the maximum voltage. Victron does not have it listed here. In the manual, it might be listed out more specifically, but it's in the model number. The MPPT 100 stands for 100 volts. It'll handle 100 volts max. Same thing on the other side, 100 volts max. The name also has the 20, which is our charging current. This one, it might be a little bit confusing. Just kind of like let it sink in, and it'll make more sense as we go through explaining more advanced videos. There's two different numbers here. The rated charge current. This is the amount of power that the MPPT can send from itself to your battery. This is how fast it can charge your battery. The max PV short circuit current. This is the amount of power that can come from your solar panels to the MPPT before it reaches its maximum limit. It just so happens to be that they are the same number, and oftentimes they are the same number or they're very close together, but they are not the same thing. So that's why Victron's nice enough to list them both for you. I don't know if I want to drop something advanced just yet, so I won't do the math, but I just want to point out something that again is a foreshadowing element. You can see battery voltage matters when it comes to power, and it has to do with what we just talked about, the amps. If your amps are your limit, in this case 20 amps is your limit, and wattage is equal to amps times volts, then the higher voltage system you're working with, the more wattage you can get out of it. And that's why you see these figures changing. So you can actually get more solar power from the exact same MPPT if you have a higher voltage battery system. Something to keep in mind. So to recap on Victron, 100 volts would be our max, 20 amps would be our max, and we know that it's compatible with lithium batteries, and we know that it's compatible with these voltages, or these voltages, whichever one we chose for the example. And I would always go with the 48 volt, so that would be the one I would choose. We can go ahead and move on to our next practical example. So now I've gone completely the opposite way with this. Instead of a tiny little standalone MPPT like I have on the wall, this is a big whole home FlexBoss all-in-one. Well, actually, this is an 18 kPV from EG4. So it's a big all-in-one inverter, and it's such a high-powered system that it actually has 3 MPPTs built into that one box. But it's like I said, whatever comes up first, that's what we'll grab. Let's go hunt down the exact same figures that we were just looking for. Let's start with the maximum voltage. It's actually quite clearly notated on here, right here. DC input voltage range, 100 to 600 volts. So we know that 600 volts is our maximum on this one. Next thing we need to find is our maximum amps. Well, it's right here, max short circuit current input. It is listed 3 times because we have 3 MPPTs. And you can see they are not all the same either. This has one larger MPPT, so you can put one very large high-powered array, and then it has 2 smaller ones so you can supplement it. So that would be the figures you would need, depending on which MPPT that you're currently connecting to. Use the right one. And the last thing is, what voltage does it use? I can tell you just from knowledge, again, this is why you might have to go look at the white papers or the manual. These big all-in-one whole home systems like this, they exclusively and only support 48 volt systems. So that's the second example. I know I actually missed the PowerPoint and I didn't update that. And with our second example done, I think it's time to go ahead and now move into doing the math. So, I mean, we've covered the source with the solar panels, what specs we need to get from the solar panels. We've covered the destination, which is the MPPT, and what specs we need from there. Now, how do we figure out what works and what doesn't work? And that's just a matter of simple math. So I'm going to apologize up front if you hate math, because it seems like most people do. I don't hate math. I'm a STEM guy. Math and science is my thing. Spelling is my worst thing. I can't spell anything. And funny enough, though, I almost failed Algebra 1 in high school, even though I'm good at math. And then after I got an F in algebra, I was put into honors calculus and I got an A+. It was just a bad teacher. So at any rate, we're going to do math. I promise you it's not that hard. And because this is our first introduction video, I'm going to be keeping it a little bit simple. There's different ways to wire solar panels together. Today, we're going to be covering the simplest form of hooking them together, which is series. Let's actually do a diagram again. I think it's best to explain everything in detail. If we got 3 solar panels, I'm not going to go into parallel yet, but I just want to make sure you know what series is. Every solar panel is going to have a plus and a minus lead coming off of it, the power cables. So your positive side, your negative side. And you have more than one solar panel, you need to hook them together. The right way to do this when you want to hook them in series is you would stagger them in such a way that the negative from one connects to the positive of the other, the negative one connects to the positive of the other. That's going to leave you with 2 leads left over, 1 positive lead, 1 negative lead, and this would go to your MPPT. So this MPPT would have access to all 3 of these solar panels in series. And what happens when we're in series is our voltages add up. So if these were 20 volts each, this would be seeing 60 volts at the MPPT. So that's what a series connection does. And the one thing I want to talk about is safety. Let's talk about the most important thing I have on this page is safety. Solar panels obviously are not a static performing thing. The position to the sun, the sunlight, the weather, everything affects how much a solar panel produces in a given time. Most of the time it's going to perform under its maximum spec. But there are rare occasions where it performs higher than its maximum spec. It actually can happen. And some people that don't know this exists, and if they were to size their panels to the max and not leave some safety, they might be okay for a while, but one day they're going to get very unlucky and their systems, in the best case scenario, are going to go into an error state, but in a worst case scenario, it could literally fry. It could get damaged and never work again. So we leave a safety. Let me just talk about safety first before we move into the math. Safety. How do you determine this percentage, this 10 to 20? It's just kind of a golden rule for those who are keeping the math simple. I live in Florida. I'm near the equator. I'm in a tropical climate, so it is hot most of the year, and then we have pretty mild and brief winters. It's the cold weather that is the number one enemy of making these solar panels produce extra voltage. So in Florida, I'm really safe with that 10%, which is the bottom of that, that range. But if I lived up in somewhere where it's icy and snowy and cold, I would be going closer to that 20% figure. Just keep this in mind too. Not so much with your power stations, your all-in-ones, but if you're doing a system where you're building it piece by piece like I did over there on the wall, there's a reason why there's 2 MPPTs on the wall. You can have more than one MPPT working together to charge your batteries. And doing so means I was able to leave that proper safety, but still keep increasing the amount of solar that I use. All right, so how do we do it? It's really easy. We're going to just be taking the solar panel VOC and adding it for each panel until we get that number. And then whatever that number is, we want it to be under the max. It's pretty much everything we discussed, but let's actually go put it to practice. So here we are with our very first practical example using the exact same items we already looked at. So let's just recap. If we were using this solar panel, the numbers we need are the 48.9 for the VOC, the 11.4 for the LSC, 600 volts for the maximum MPPT voltage, and we have a maximum amp based on which MPPT that we're using. So we're just going to use the 19 amp one as the example. So with those numbers, let's see about finding a way to do math on screen. Let's start with our 600 volts. Let's actually start with making that bigger. There we go. 600 volts. And we need to add our safety. So in my case, the safety of 10%. I can mental math that, but let me show you how you would do that math. So you would have 2 ways to do this, or probably more than 2. Math's awesome, and that way you can do it 500 different ways. As long as you get the answer, that's what matters. So you can say times 0.1, which is equivalent to 10%, and you would get, in this case, 60. And that's what 10% of 600 is, and you would take 600 and minus 60, and you'd get 540 volts. Or you can do that kind of the opposite way. You can say 600 times 0.9, which is 90%, and you would get the answer right away. Although I'm decent at mental math, I can't do 600 times 0.9 in my head. If you can, congratulations. But that's our figure we're going for, 540 volts. That's our maximum with our safety. So I'm just going to put that back up here again. Now it's pretty easy. You can add them one by one if you want. So we can take the 48.9 volts and just keep adding it and adding it until we get to that figure. Or, we have calculators. It's not a shame to do anything with a calculator. So take 540. Well, let's not put equals there. It's 540 divided by the 48.9. And that will tell you how many solar panels you can use. So I actually did the math off screen. I'm just going to pull it up and show it to you. And we'll talk about it, make it easier to understand. So 420 watt panel, holy cow, that's a big arrow. We made note of our VOC and our LSC. I had to determine my safeties. So I took that 600 and I did it for both. I did the 10% and the 20%. So 10% would be 60, 20% would be 120. And then your final numbers would be 540 volts would be your safety for 10%, and 480 volts would be your safety for 20%. So I went with 540, then I divided it by the VOC, and I got 11.04 panels. That is such a super close number. I mean, like 0.0, that I'd be okay rounding to 11 solar panels. It's actually almost exactly a perfect fit to do 11 of these panels for that MPPT. So that was a really awesome first example. And now we're going to actually go to the next example, which is going to work out completely differently. Okay, so let's move on to our second and final example. We're going to be using the remaining solar panel and the remaining MPPT that we already looked at. We'll recap on our specs. So the solar panel, we're interested in the VOC 47.7. We're interested in the LSC of 11.51. And we're interested in the maximum voltage from the MPPT of 100 volts and the maximum amps of 20. We'll go back and do our math, same as before. 100 volts is our max. So we need to figure out what 10% of that is. Mental math for me is, like I said, okay. I think most people work with 100. It's pretty easy. So we just know that's going to be 90. Of course, if you wanted to figure that out, it'd be 100 times 0.9 for 90% of 100, which would take away 10, or 100 times 0.1, and then you'd get your 10 as your answer, and then subtract 10 from 100 to get 90. I think I'm definitely dyslexic, by the way. Even though I'm really good with numbers, I do swap things up, especially when I'm thinking faster than I can type or write. So that's how you get your safe value. So we've got 90. And now we're going to do the math. So it'd be 90 volts divided by the VOC of 47.7. And just like before, I actually worked out the math off screen, so we can just go over that and make it a little bit easier to view. So this is going to be the 370 watt panel. That was a typo. So we've got the 47.7 for the VOC, the 11.51 for the LSC. We're going to do our safety again. So we started with 100, and we said we're going to take away 10%, which leaves us with the remaining safe value of 90 volts. And then we're going to take that 90 volts, divide it by the VOC, and you can see 1.88 panels. This is an example of a badly matched system. You do not have enough headroom to hook up two of these panels together in series and be safe. If you were just going camping, if it was just a temporary setup where you're going to have it out there for a few hours and you're keeping an eye on it, you know what the weather conditions are, then yeah, you could probably get away with it. But where it would not be safe and it would be a bad idea is if you're going to be mounting this on your roof, where it's going to be a permanent setup that sits outside 24/7, 365, and it's always going to be exposed to whatever random weather elements are out there. So we would only be able to use a single solar panel in this configuration safely. And that would be quite a bit of waste, because here you can see This is a 370 watt panel. Assuming that we used a 48 volt system, this MPPT could support us with a maximum of 1,160 watts of power, and we're only going to be making use of a maximum of 370 watts of power. So that is not very good, and that is why you want this kind of knowledge. However, this is also a very, very good precursor to the next video. The next video, we're going to take everything we learned here about series connections, and we're going to expand that knowledge to also include parallel connections. Parallel connections are useful in many, many reasons, whether it be fighting shade, or it's actually very useful in this specific case where we have run out of voltage, we can't go any higher, but we still have the maximum of 20 amps, and we're only making use of about 12 amps. So that means we can add more solar panels to this in parallel to increase this 370 watts and make it something better. So in the next video, we'll come back and we'll redo this exact example and show you how to make it better. And we're going to get into parallel and really explain what that's all about and how it can help you. So once again, this video, let's go ahead and jump to our last slide. And then we'll get into all about parallel in the next video. So ensure that you have the correct data to figure out your sizing. You saw there's lots of different numbers there. They can be similar to each other, but they are not the same. So do know the difference. Even if you're not doing the math yourself, or you're not just working out this project on your own, and you would like to go online to Reddit or Facebook or the DIY solar forums and get help from somebody, now you know how to get help. Because the biggest problem I saw was the brand new people not even knowing how to ask a good question. So now you know what data you need to give other people so they can help you. So that's a very important thing. And that's why I hope this video starts to circulate, because it's just going to make the whole community, the community is going to be tighter knit and be more effective if we work like that. Next is what I said earlier. These specs are not usually advertised because they're not advertised figures. They are the white papers. They are in the manuals. So you might have to go look in technical places or technical documents to find them. And lastly, just make sure you come back and see the next video in the series, because I'm going to try to teach you the next step in understanding everything that we talked about today, which is enhancing your knowledge to understand how parallel connections work and how they can enhance your configurations. So once again, this was Patrick from Fish's Computers, and I'll see you in the next video.